So to get to the equation of the plane, same thing again. If I start at the same point, which is what would be the orientation of the plane? The equation, the issue becomes, how can we possibly orient a plane in 3 space? So in other words, if this is a plane, for instance here, this is one plane, what is the angle that this plane makes, in fact, and with what axis? As opposed to, say, for instance, a different plane like this one. Okay, what is this one, or this plane? So the issue becomes, these different orientations of the planes, of these 3 planes even, are how do we get a handle on what, how do we get control or get a mathematical feel for what is this slope idea, like in the case of a line, what is this orienting of the plane? Well, there's a very interesting idea related to planes, and that is that of the normal vector. The normal to a plane, okay, the normal, okay, to the normal vector to a plane is something that is orthogonal to the plane. And in fact, it is orthogonal to every single vector in the plane. So in other words, if we look at this plane, there's a vector here and a vector here and a vector here, and there could be billions or trillions and infinity of vectors here. Each one of these vectors is in fact normal, is perpendicular to the normal vector that you see here, this vector. It's normal to this vector. So now, that's not the main thing. The main interesting thing here is the normal to the plane is, in fact, a very interesting and powerful idea. Very powerful idea. Because what it can do is, if you look at the normal here, this is the normal to this plane. This is the normal to this plane. So you can see that as we change, for instance, here's another plane. Okay. Say for instance this way, and this is the normal to this plane. Okay, so the question is, the interesting thing is that if you look at the angle of the normal, in other words, try to imagine the normal without the plane, and you can see that or imagine imagine gripping this in your hand, or this, and then turning this entire, you can basically hold almost, if you could, for instance, hold this normal vector and turn it around, you could in fact turn around and look at different planes. So the normal vector is a very nice little way to represent this orienting of the plane itself. So now that we have that kind of new idea sort of understood, let's get to some of the nitty-gritty. So the normal vector, let's call it the vector ABC, is the normal vector, and usually we use the letter N to represent it. Now say that we have any plane. Here is, suppose, a plane in 3 dimensions, and let's say we have a point. Let's call this point P0 again, like before. And let's say we have some arbitrary point in the plane, which is the point P. So again, P0 and P are the same as before. P0 has coordinates x0, y0, and z0, and P has coordinates x, y, and z. Now the vector, this vector here is in fact the same as before again, which is it's P0, it's P minus, or P0P is in fact, the vector P0P is in fact x minus x0, y minus y0, z minus z0. Okay, so now the question is, if this is a vector in the plane, any vector in the plane, okay, what ensures that it is in the plane? If it is a vector in the plane, then clearly the dot product, the normal to the plane would be this vector here. Okay, this would be the normal to the plane. What is the interesting relationship between these two? As I already said, in theory, the normal to the plane is perpendicular to every vector in the plane, which means that n is in fact perpendicular to P0P. Okay, perpendicular to it. So let's write both of these in their component forms, or as we did before, if you like, we can go back to a coordinate system as we had before and look at the r minus r0 representation. We could do that. So for instance, in that case, let's assume here are our axes, and this would be the vector r0, and this would be the vector r. So now you would again have the same situation, which is this would be then equal to n dot r minus r0 as earlier. Okay, so now what happens is, now what's going on is that this in fact must be equal to 0. Why? Why is it equal to 0? Because the normal vector n is perpendicular to the vector, to any vector in the plane, and r minus r0 is any vector, is a vector, sorry, in the plane. Now, what we do from this is, now this relationship can give us a very simple equation of the line, equation of the plane, sorry. Let's write these in component form. So we are talking about the dot product of ABC with x minus x0, y minus y0, and z minus z0. Okay, and that's supposed to be equal to 0, which means that we end up with a into x minus, let me just make some space here. Sorry about that. Okay, so, and I'll move it down here. Okay, so x minus x0 plus y, I'm sorry, pardon me, plus b into y minus y0 plus c into z minus z0 is equal to 0. This is a algebraic equation, and in fact it can be written as ax plus by plus cz minus you have here ax0 plus by0 plus cz0, and this is all equal to 0. This is the equation of a plane, and which we've just now written down here. What's interesting that I want you to note about this immediately are these three values, and you will notice that this is in fact the normal. The normal is a, b, c. So this means that if I had any equation of the plane like 2x plus 3y minus 4z plus 19 equals 0, now this is equation of any plane, then in fact these numbers here okay, means that the normal to this plane is 2, 3, minus 4. So immediately by this definition of the equation of a plane, or this expression of the equation of a plane, we can read off in fact immediately information, like we can in the case of y equals mx plus c. We know that m is the slope of the line, and therefore gives us an idea about the orientation. Here the n in fact is the normal to the plane and gives us a clear indication of the orientation of the plane. So basically what we've done now is we've gotten a way where we can in fact look at the equation of a plane and the equation of the line. An example of how to find the equation of a plane given a point 1 minus 5, 7, and this is the point and the normal, and find the equation of the plane that contains the point 1 minus 5, 7, and is has an and with normal vector minus 3, 0, 5. So if we want to find the equation of such a plane, it's quite easy to do. In fact, all we do is minus 3, which is this first one here, x minus 1 plus 0. I'm just going to write it for your reference. Y plus 5, and then plus 5 into z minus or z minus 7 equals 0. Simplifying, of course, it boils down to minus 3x plus 5z, okay, and plus 3 minus 35, which is minus 32, is equal to 0. So that's the equation of the plane. More interesting a question could be, for instance, given any 3 points. So for instance, if we were given 3 points, say for instance 0, 0, 1, and B was, for the sake of argument, 2, 0, 0, and C was, for instance, 0, 3, 0 for the sake of argument. And we were asked, what is the equation of the plane that contains these 3 points? Well, keep in mind that from these 3 points, since they are in the same plane, clearly we could easily construct the vectors AB, okay, and the vector AB in this case would be 2, 0, 1, and the vector AC, okay, 2, 0, minus 1, pardon me, and the vector AC would be 0, 3, minus 1, okay? So now, if I were to take the cross, so these are 2 vectors, AB and AC, that lie in some plane for the sake of argument. So say like this. So this is A, and this is B, and this is C. So these are 2 vectors. So now, if I take the cross product of these 2 vectors, so in other words, AB cross AC, that vector is clearly going to be the normal to the plane because it's going to be perpendicular to these 2 vectors and in fact is normal to the plane. So how we calculate, just to remind you, using the determinant method is as follows. Okay, and that becomes, so basically it's the vector 3, 2, 6, and the vector 3, 2, 6, this is the normal to the plane. So therefore, all that remains then is to choose one of these 3 points, and let's choose the first one there. Let's choose A as the point. So we have x minus 0, and it's multiplied by 3 plus 2 times y minus 0 plus 6 times z minus 1 equals 0 as the equation of the plane, which means this implies we have 3x plus 2y plus 6z minus 6 equals 0 is the equation of this plane. All right, and again you can see 3, 2, 6 clearly there as a normal to the plane. So that's all I want to say about finding equations of lines and planes in 3D. There can be other examples, of course, which you can explore in your own time. Thank you.